All right, let's just dive right in. Today, we're shrinking way, way down into a world that is literally all around us, but completely invisible. This is the world of nanotechnology. And trust me, this isn't going to be some dry science lesson. This is a journey into a hidden place where the basic rules of physics, well, they start to get a little weird, and the possibilities are absolutely mind-blowing. Let's go. Okay, so to even wrap our heads around this stuff, we have to completely reset what we think of as small. So let me just ask you, how small is small, really? Because we're about to go on a zoom in so fast and so extreme, it's almost impossible to picture. All right, so let's ground ourselves with something we all know. Us. The average person is about, 1.7 meters tall, give or take. Simple enough. This is our starting point. Now, take one single strand of your hair. To us, it's super thin, right? But on the scale we're headed to, that one little hair is suddenly this massive skyscraper. We're talking about 100,000 nanometers wide. And there's our magic word for the day, nanometer. So what in the world is a nanometer? Well, officially, it's 1 billionth of a meter, which, doesn't really mean anything, right? It's just a number. But check out this analogy. It's perfect. Imagine a golf ball. Now imagine our entire planet. The size difference between a tiny nanometer and that golf ball, it's the same as the difference between that golf ball and the entire Earth. Yeah, that's the world we're diving into. Okay, so we've arrived. We're at the nanoscale. But listen, this isn't just about making things tiny. This is where it gets really wild. Down here, at the level of individual atoms, the fundamental rules of how stuff works, they start to change in really cool and unexpected ways. And you might think, okay, this has got to be super complicated, right? Well, yes and no. The crazy new abilities of these nanomaterials, there's superpowers you could call them, they mostly boil down to one single core idea, one property that changes absolutely everything. And this is it, the big secret, surface to volume ratio. Think about it like this. Picture a big cube of sugar, right? It's got 6 sides, that's its surface area, and a whole bunch of sugar packed inside, that's its volume. Now, what happens if you smash it into thousands of tiny little grains? You've still got the same amount of sugar, the same volume, but you've just created thousands of new surfaces. You see? The surface area just exploded. Well, at the nanoscale, this effect is just off the charts. Almost every atom is on the surface, ready to interact with the world. And that is the whole game. This massive surface area unlocks completely new properties. Things we thought we knew about a material just flip upside down. Take gold. Gold is, well, it's golden, right? But break it down into nanoparticles, and suddenly it can look red. Why? Because it starts playing with light in a totally different way. The very same material can get all these new optical, electrical, magnetic, and structural powers just because we made it small. So this stuff is obviously amazing, but how in the world do you make something that small? I mean, you can't exactly use a tiny little hammer, right? Turns out there are 2 main ways to think about it, 2 different philosophies. On one hand, you've got the top-down approach. This is exactly like a sculptor. You start with a big block of stuff, and you just carve it down. You chip away, you etch it, you blast it, until you're left with something nano-sized. Then you've got the total opposite, bottoms up. And this is just like playing with Legos. You start with the tiniest possible pieces, individual atoms and molecules, and you click them together, one by one, to build exactly what you want from scratch. So let's get real for a second. What does a top-down method like ball milling actually look like? Well, it's surprisingly simple, almost brutal. You basically take your material, throw it into this big drum with a bunch of heavy, hard balls, and then you just spin the heck out of it. The balls just smash and crash into the material over and over again, mechanically grinding it down into a super fine nano-sized powder. It's brute force, just on a ridiculously small scale. Okay, so you've made your nanoparticles. Great, but how do you know? How can you possibly see what you're doing when you're building with atoms? You can't, not with your eyes. You need a whole new kind of vision. You need some seriously powerful microscopes. And 2 of the big guns here are the SEM, the Scanning Electron Microscope, and the AFM, the Atomic Force Microscope. Think of the SEM as a way of seeing. It shoots a beam of electrons at the surface and builds a picture from how they bounce back. But the AFM, the AFM is something else. It literally feels the surface. It has this incredibly sharp needle that it drags across the material, and it can feel the individual bumps of single atoms. It's not just a picture, it's a 3D map. It's as close as we can get to actually touching an atom. And the power of these things, it's just hard to even comprehend. We're talking about magnifying something up to 1,000,000 times. 1,000,000. This isn't just zooming in, this is pulling back the curtain on a layer of reality that for all of human history was completely invisible. We can now see the building blocks of everything. So we can make it, we can see it, but what's the big deal? Why does all this matter in the real world? Well, this is where all that mind-bending science suddenly becomes a full-blown revolution for pretty much everything. I mean, the potential is staggering. We're not just talking about small improvements. We're talking about creating brand new materials, stronger than steel but as light as plastic. We're talking about electronics, building computer chips so tiny and so fast they'll make today's tech look like a horse and buggy. And in medicine, imagine tiny robots, nanoparticles, that can hunt down a single cancer cell in your body and deliver medicine right to it without touching any healthy cells. Or building better batteries, better solar panels. The list just goes on and on. So this is where we are. We're standing at the very beginning of a new age. For the first time ever, we're not stuck with just the materials we can find in nature. We are actually learning how to be architects at the atomic level. The power to build our world, literally atom by atom, is becoming a reality. And that just leaves us with one gigantic question. What should we build first?